Welcome to the Explainer. Today we're going to tackle one of the trickiest bits of vector geometry, finding out if and where two lines actually cross in 3D space. So here's what we've got on deck. First, we're going to visualize the three main ways lines can behave in 3D. Then, and this is the big one, we'll walk through a foolproof algorithm that tells you for sure if lines are intersecting or skew. And finally, we'll put that tool to the test with real textbook problems and exam questions so you're ready for anything.
All right, let's get into it. When you've got two lines just kind of floating around in 3D space, things get way more interesting than on a flat piece of paper. You've basically got three different scenarios that can play out.
Yeah, it sounds simple enough, right? But that third dimension, it adds this really cool twist that you just don't get in 2D. So let's break down what can happen. Okay, so first, the lines can be parallel, like train tracks running alongside each other, never ever touching. Second, they can intersect, crossing at one single point. And then there's the third option, and this is the one that only happens in 3D. They can be skew. Now, parallel lines are pretty easy to spot. The real challenge, and really the whole point of our algorithm today, is telling the difference between intersecting lines and skew lines. They're both not parallel, but what happens to them is totally different. Skew lines can really mess with your head. Just picture two airplanes. They're flying at different altitudes on completely different paths. If you look down from space, it might look like their paths cross, but they're in different layers of the sky, right? They'll never actually hit each other. That's exactly what skew lines are. And this really nails the fundamental difference. For lines to intersect, they have to be on the same flat surface, the same plane. But skew lines, by their very definition, they're not. So a collision is totally impossible because they're living in different parts of that 3D space. Okay, so we get the idea, but how do we prove it with math? How can we know for sure if two lines are intersecting or skew? Well, what we need is a system, a step-by-step process, an algorithm that gives us the right answer every single time. And this four-step algorithm is that tool. So we use these things called parameters, usually little Greek letters like lambda and mu, to describe any point on a line. Steps 1 and 2 are all about setting up your equations for x, y, and z and making them equal. Then for step 3, you just use two of them, like x and y, to find the one possible spot where they might cross. And then step 4, well, that's the moment of truth. You check, does that spot also work for the z coordinate? If yes, boom, they intercept. If no, they're skew. Simple as that. Okay, theory is one thing, but let's see this thing actually work. We're going to jump into some classic examples straight from the textbook and see how this all plays out with actual numbers. All right, first up, example 9.13. And this one is kind of nice. They actually give us a heads up and tell us the lines do intersect. So our job is just to prove it and find out where. It's the perfect way to test out the algorithm. So just like we planned, we make the x, y, and z parts equal. We solve the first two equations together and get our potential parameters. Lambda is -1 and mu is 1. Now for the big moment, checking that third equation. Okay, now let's flip it. For example 9.14, we have to show the lines don't intersect. And since we can see their direction vectors aren't parallel, well, if they don't intersect, they've got to be skew, right? And here it is, the moment of truth for this one. We do the exact same thing, solve for our parameters using two equations. But this time, when we do the check, when we plug those values back in, we get two totally different points. The coordinates just don't match up. There's no single point where they meet, so the check fails. These lines are skew. So, we've seen the algorithm handle a couple of specific cases. Now, let's zoom out a bit and look at a summary from a whole exercise set. You'll see how this one process can figure out every possible relationship between two lines. This little table from exercise 9E is perfect. It really shows off how powerful this algorithm is. Using the exact same 4 steps, we can figure everything out. In parts A and D, the check fails, so we know they're skew. In part C, it passes, and we find the intersection point. And get this, in part B, it turns out the lines are actually the same line. So they intersect at infinite points? Okay, but this isn't just some abstract math exercise, right? This algorithm is a tool. And exam questions, that's where you really learn to use that tool when it counts. Let's look at a couple of typical exam-style problems. Here's a classic one. They ask you to determine if two lines are skew. Now remember, to prove lines are skew, you have to prove two things. 1, they're not parallel, and 2, they don't intersect. It's always a two-part test.
So first things first, we check the direction vectors. You can see pretty easily they aren't multiples of each other, so okay, they're not parallel. Now we run the intersection algorithm, we set the components equal, and look at that, the z equation tells us s has to be -1. If we plug that into the other equations, we get a consistent value of t equals 1. The check passes, so the lines intersect, which means, of course, they are not skew. Okay, let's try a trickier one. Here, they tell us the lines can meet, but we have to find the specific value of some unknown variable p that makes it happen. This is a really good way to test if you truly get it.
So the logic is kind of flipped on its head here, but the process is exactly the same. We start by assuming they intersect. That lets us use the x and y equations, the ones that don't have p in them, to find the exact lambda and mu that would make them meet. Turns out lambda is 3 and mu is 6. All we have to do now is plug those values into the z equation and solve for our mystery p, and we get p equals -80.
Wow, okay. We've gone all the way from the basic ideas to some pretty tough exam problems, but it's all been built around one single idea. So let's boil all this down to the one key takeaway. Look, if there's only one thing you remember from all of this, make it this: trust the algorithm. Seriously, that fourth step, the check step, it's not optional. It is the definitive, conclusive test that tells you if lines are intersecting or skew. It's the mathematical proof, and it will give you the right answer every single time.
So there you have it. You now have a rock-solid method for dealing with two lines. The principles we used here are going to be super useful as you move forward, which leads to the next big question, right? What happens when you try to intersect a line and a plane? Thanks for joining me on The Explainer.